Something beneath the chaos of the cosmos feels strangely arranged. You look at a swirling galaxy, the spiral of a seashell, even the branching of a tree, and a quiet question whispers. What if these aren't just accidents? What if they are clues to a hidden order, a vast and intricate pattern woven into the fabric of everything? Today, we are going on a journey to uncover exactly that. We will explore 30 of the most mind-bending theories scientists have proposed about the universe's secret blueprints. By the end, you will see reality in a completely new light, questioning the very nature of what is real. We will investigate if our universe is a hologram, a simulation, or part of an endless cycle of rebirth. We will ask why the laws of physics seem perfectly tuned for life, and what mysterious force is pulling entire clusters of galaxies toward the unknown. So, are you ready to look behind the curtain of existence? The first clue is written in the stars and in the petals of a flower. It is a simple series of numbers 1, 1, 2, 3, 5, 8, 13, and so on, where each new number is the sum of the two before it. This is the Fibonacci sequence, but its true magic is not in the numbers themselves. It is in the shape they create when you draw quarter circles through squares based on these numbers. That shape is the Fibonacci spiral, a curve of breathtaking perfection that appears with an eerie consistency across our reality. Look at the center of a sunflower. Its seeds are packed in a stunning, radiating pattern of interlocking spirals. Count those spirals and you will find they are always Fibonacci numbers like 34 and 55 or 55 and 89. This same spiral unfolds in the arrangement of pinecone scales, the curl of a nautilus shell, and even the branching of trees. It is a pattern of optimal growth, a way for nature to pack the most material into the smallest space. Then look up. The grand design spiral galaxies like our own Milky Way often follow this same logarithmic spiral, their arms unwinding in a curve that mirrors the one in the seashell on a beach. The scale is unimaginably different, but the geometry feels hauntingly familiar. This connection is often described through the golden ratio, a special number roughly equal to 1.618 that appears when you divide consecutive Fibonacci numbers. It is a proportion considered aesthetically perfect, found in the Parthenon, great works of art, and the proportions of the human body. So what does this mean? To some, this is the signature of a cosmic architect. It suggests a fundamental geometric blueprint, a single mathematical rule guiding growth from the microscopic to the galactic. The universe, in this view, is not random chaos but a grand fractal artwork built upon repeating patterns. Others, however, hear a different story. They argue this is not evidence of design but of efficiency. The Fibonacci spiral is simply the most effective way for things to grow under physical constraints, a pattern that emerges naturally from simple rules, like maximizing sunlight on leaves or structural stability in a shell. In this interpretation, the pattern is a beautiful accident of physics, not a deliberate message. This is the core of our mystery. Is the Fibonacci sequence a whisper of intentional design woven into the cosmos, or is it just the universe finding the same elegant solution to a common problem over and over again? The answer changes everything about how we see our place in the pattern. But if patterns in nature leave us wondering, the oldest light in the universe presents us with a genuine cosmic shock. This light is the cosmic microwave background, a faint glow that fills every corner of the sky. It is the cooled and stretched remnant of the fireball of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. For decades, this cosmic afterglow was hailed as the ultimate proof of the standard cosmological model. When we finally mapped it in exquisite detail, scientists expected to see a near-perfect, smooth distribution of tiny temperature variations like the static on an old television. The universe, they believed, should look roughly the same in all directions, a fundamental assumption called isotropy. but the map told a different story. It revealed strange, large-scale asymmetries, cosmic wrinkles that should not be there. The most famous of these is nicknamed the axis of evil. This is not a literal axis of destruction, but a startling alignment. The patterns of hot and cold spots in the cosmic microwave background appear to line up in a specific, preferred direction across the sky, almost as if the entire universe has a tilted orientation. It is as if you walked into a room painted to look perfectly random, only to realize all the brushstrokes subtly point toward one corner. Then there is the cold spot, an enormous region of space far colder than our models can easily explain. It is a giant, mysterious bruise on the face of the early universe. These are not minor quirks, they are profound anomalies that directly challenge the cornerstone principle of cosmological uniformity. So what could they mean? One radical idea is that these asymmetries are scars from a time before our Big Bang, imprints from a previous cosmic cycle or a collision with another universe entirely, a multiverse bump that left a permanent dent in our reality. Another possibility is that our universe is not alone but is part of a vast, lopsided structure on scales we can barely comprehend, like a single brick in a wall that curves away into the darkness. The most conservative explanation, of course, is that there is a flaw in our observations or in our interpretation of them, a subtle bias we have not yet accounted for. But if these anomalies are real, they force a humbling conclusion. The universe on its largest scales may not be the uniform, isotropic place we assumed. It may have a preferred direction, a cosmic north, and contain structures so vast they defy our current physics. The oldest picture we have of everything might be telling us we have misunderstood the frame it sits in. These cosmic asymmetries are not the only large-scale surprise. Zoom out from any single galaxy, and the universe reveals an even grander architecture. For most of human history, we imagined stars and galaxies scattered like lonely islands in a vast, dark sea. The truth is far more structured and strangely familiar. Galaxies are not isolated. They gather into immense clusters, and those clusters are linked together in sprawling, thread-like filaments, forming a colossal three-dimensional web that stretches across the observable universe. This is the cosmic web. Between these brilliant filaments lie the cosmic voids, unimaginably empty regions of space spanning hundreds of millions of light-years, some nearly devoid of galaxies altogether. It is a sponge-like structure on the grandest possible scale. This web was not drawn by a celestial cartographer. It is the result of a slow, relentless sculptor, gravity, working on an invisible canvas. Scientists believe that after the Big Bang, the universe was not perfectly smooth. It had tiny, random ripples in density, like the surface of a pond after a light rain. Over billions of years, gravity amplified these ripples. The slightly denser patches pulled in more and more matter, both the ordinary matter we see as stars and galaxies, and the mysterious, invisible substance known as dark matter. Dark matter, which does not emit or reflect light, is thought to form the underlying skeleton of this web. Its gravity provides the scaffolding upon which ordinary matter condenses and lights up, tracing out the luminous filaments we can observe. The pattern that emerges is not random. It is a complex network of nodes and connections, and for many who look at it, a profound sense of recognition stirs. Take an image of the cosmic web and place it beside a map of the neural networks in a human brain. The resemblance is startling. Both are intricate, filamentary structures with dense clusters of activity, the galaxy clusters and the neuronal bodies, connected by long, thin threads, the cosmic filaments and the synaptic axons. Both systems organize matter and energy to transmit information, in one case light and gravitational waves, in the other electrical and chemical signals. This visual echo has led to a provocative theory. Perhaps the universe is not just building galaxies and stars. Perhaps it is naturally inclined to form these specific, web-like patterns whenever a complex system evolves under the influence of a dominant, attractive force, whether that force is gravity or the electrochemical impulses driving a biological brain. It suggests a kind of universal grammar for complexity, a fractal principle where the same basic pattern repeats from the microscopic wiring of our thoughts to the macroscopic scaffolding of the cosmos. The cosmic web, then, might be more than just a structure. It could be a signature, a hint that the universe organizes itself according to deep, mathematical rules that manifest across wildly different scales and forms of existence. We are not just living in the web, we are, in a very real sense, made from the same pattern. This eerie repetition of patterns leads to an even more fundamental question. Why does the universe allow for such intricate structures in the first place? The answer lies in a set of cosmic dials, fixed numbers that dictate the behavior of everything. These are the fundamental constants of physics. Think of them as the immutable settings of reality, the gravitational constant, the strength of the electromagnetic force, the mass of an electron. They are not predicted by any theory, they just are, and their values are not just arbitrary, they are, to a staggering degree of precision, perfect for our existence. This is the mystery of fine-tuning. If the gravitational constant were just a tiny fraction stronger, the universe would have collapsed back on itself immediately after the Big Bang in a catastrophic crunch. A fraction weaker, and matter would never have clumped together to form stars or galaxies at all, leaving a cold, dark, eternal fog. If the strong nuclear force which binds atomic nuclei together were even slightly different, hydrogen would not fuse into helium. Stars would never ignite. The universe would be a sea of inert hydrogen with no heavier elements like carbon or oxygen, the very building blocks of life. The cosmic recipe for a living universe is written in these numbers, and the margin for error is vanishingly small. It is as if a cosmic locksmith crafted a lock with a billion possible combinations, and the universe we live in is the one and only key that fits. So how do we explain this breathtaking precision? Scientists have proposed two profound and deeply contrasting interpretations. The first is the multiverse theory. This idea suggests our universe is just one bubble in an infinite froth of universes, each with its own random set of physical constants. In most of these universes, the numbers are wrong. They are stillborn or barren or collapse instantly, but by the sheer, unimaginable law of large numbers, a few universes purely by chance get the numbers right. We, of course, find ourselves in one of those rare, habitable bubbles, not because it was chosen, but because we could not exist anywhere else. The other interpretation is the anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers. It is a logical tautology that feels deeply unsatisfying yet profound. It does not explain why the constants are fine-tuned, only that if they were not, we would not be here to ask the question. Some take this further, suggesting the fine-tuning is evidence of a cosmic purpose, a universe intentionally calibrated to give rise to conscious life. This is not necessarily a religious argument, but a philosophical one pointing toward a teleology, a direction or goal built into the fabric of existence. The fine-tuning of the constants presents us with a stark choice. Is our universe a miraculous, one-in-a-billion fluke, a lucky ticket in a cosmic lottery of infinite, mostly dead universes? Or is the precision of these numbers a whisper of something deeper, a hint that the cosmos is not just a random accident, but a stage set with astonishing care for the drama of life to unfold? The dials are set, the question is who or what turned them. The fine-tuning of the universe feels like a puzzle with pieces that fit too perfectly. But what if those pieces and the three-dimensional world they build are not the whole picture? There is a theory so radical it suggests our entire reality, with all its stars, planets, and people, might be a magnificent illusion. This is the holographic principle. It proposes that all the information contained within any volume of space, like the room you are in or the entire observable universe, can be completely described by information encoded on its two-dimensional boundary. Think of a hologram on your credit card. The flat, shiny surface holds all the data needed to project a stunning, three-dimensional image that seems to have depth and solidity. The holographic principle suggests our universe might work the same way. We could be living inside a cosmic projection, with a true, fundamental reality existing on a distant, two-dimensional surface, perhaps at the very edge of the cosmos. This idea did not come from science fiction. It emerged from the most extreme environments we know, black holes. In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking made a startling discovery. They found that a black hole's entropy, which is a measure of its hidden information or disorder, is not proportional to its volume as you might expect. Instead, it is proportional to the area of its event horizon, the spherical surface that marks its point of no return. This was a profound clue. It hinted that all the information about what fell into a black hole was not lost inside its infinite density, but was somehow smeared and stored on its two-dimensional surface. The universe itself, some theorists began to argue, might operate on a similar rule. The mathematics of string theory, our best attempt at a theory of everything, later provided more support, showing that certain physical processes in a volume of space could be perfectly described by theories operating on its boundary. So what are the staggering implications? If the holographic principle is true, then our rich, three-dimensional experience of reality, the feeling of depth, of moving through space, of being solid objects, is a kind of elaborate decoding of data written on a flat screen at the edge of everything. Every event, every particle, every thought would be a pixel in a cosmic projection. This transforms our search for hidden patterns. The symmetries we see, the Fibonacci spirals, the cosmic web, even the fine-tuned constants might not be the primary reality. They could be shadows, emergent properties of a deeper, simpler, two-dimensional code written on the fabric of spacetime itself. The patterns we are obsessed with finding in three dimensions might actually be written in a language we cannot yet read, on the surface of a sphere we cannot yet see. Are we living inside the universe's most convincing illusion? If our reality is a holographic projection, then who or what is running the simulation? This question leads us to one of the most provocative and widely discussed ideas of our time, the simulation hypothesis. Popularized by figures like Elon Musk, it suggests a startling possibility. Our entire universe, with all its history, complexity, and conscious experience, is not base reality, but an extraordinarily sophisticated computer simulation created by a vastly more advanced civilization. Think of it as the ultimate video game where we are not the players but the characters, unaware that our entire existence is rendered in the memory banks of some unfathomable computer. Proponents of this idea point to curious clues woven into the fabric of physics itself. One is the concept of pixelation at the Planck scale. In our digital world, if you zoom in far enough on a screen, you see the individual pixels that make up the image. In physics, there is a fundamental limit to how small anything can be, a smallest possible unit of length called the Planck length. Below this scale, our concepts of space and time break down. Some argue this is not a limitation of our knowledge, but a feature of the simulation. It is the resolution of reality, the point where you see the underlying code, preventing an infinite regress that would crash the system. Another piece of evidence often cited is the universe's undeniable mathematical underpinnings. Physics is not just described by mathematics, it seems to be mathematics. From the elegant equations of general relativity to the strange probabilities of quantum mechanics, reality behaves with a logical, computable structure. This, to some, suggests a programmed environment operating on deterministic or probabilistically deterministic rules. A simulated universe would need a consistent set of laws to govern it, and mathematics provides the perfect programming language. The philosophical arguments are equally compelling. If a civilization could reach a post-human stage of technological development, capable of creating conscious simulations of its own ancestors or other worlds, then it is statistically likely they would create not just one but countless such simulations. The number of simulated beings would vastly outnumber the beings in the original base reality. Therefore, if you are a conscious being, the odds are overwhelming that you are living inside one of those simulations, not in the original world. This is a modern twist on the anthropic principle. We would most likely find ourselves in a simulated reality simply because there are so many more of them. But the theory faces fierce scientific and philosophical pushback. Critics argue that simulating every particle and interaction in a universe as vast as ours would require computational resources exceeding the energy of entire stars, making it practically impossible even for an advanced civilization. Others point out that true consciousness may not be something that can be simulated with mere code, that the rich, subjective experience of being alive, what philosophers call qualia, might be an intrinsic property of base reality that cannot be replicated. Furthermore, if our universe is a simulation, why does it contain so much wasted space, so many empty voids and barren planets? Wouldn't an efficient simulation focus only on the interesting parts where observers exist? Unless, of course, the simulation is for a purpose we cannot comprehend, or it is simply running a full historical model to see what happens. The simulation hypothesis forces us to confront a profound and unsettling pattern. It suggests the ultimate hidden order of the cosmos might not be a spiritual design or a fundamental law, but a line of code. Our search for meaning, our sense of self, even our free will, could be emergent properties of an algorithm. Whether you find this idea terrifying or fascinating, it reframes every mystery we have explored. The Fibonacci spiral, the cosmic web, the fine-tuned constants, they would not be features of a fundamental reality, but elegant subroutines in a program so vast we are only beginning to glimpse its syntax. Yet if we are a simulation, what powers the computer? Even a simulated reality needs an origin, a first cause. This leads us to a theory that redefines the beginning of everything. The story of our universe starts with a bang, a singular explosion of space and time. But what if that story has been told countless times before? What if the Big Bang was not the absolute beginning, but merely the latest chapter in an endless cosmic saga? This is the heart of cyclic cosmology, and one of its most compelling versions comes from the Nobel laureate Sir Roger Penrose. He calls it conformal cyclic cosmology. In this breathtaking vision, our universe is not a one-time event destined for eternal, cold darkness. Instead, it is part of an infinite series of cycles or eons. Each eon begins with its own Big Bang, expands for trillions upon trillions of years, and eventually dies out as all matter decays and black holes evaporate, leaving behind a universe of nothing but massless particles and radiation, a state of uniform, featureless energy. Now here is the beautiful and subtle twist. In this extremely stretched out, empty end state, the concept of scale becomes meaningless. Distances and times lose all definition. Penrose uses a mathematical concept called conformal rescaling to show that this vast, cold, empty end of one eon can be seamlessly transformed or rescaled into the hot, dense, small beginning of the next. The infinite future of one cycle becomes the singularity of the next. It is an eternal return, a cosmic phoenix rising from its own ashes, not in a violent collision, but through a graceful mathematical transformation. But a theory this grand needs evidence. Penrose and his colleagues believe they may have found it, etched into the oldest light we see. They analyzed the cosmic microwave background, that baby picture of our universe, and claim to detect strange, concentric rings within it. These rings are regions of slightly uniform temperature, like faint ripples on a pond. The provocative claim is that these rings are the gravitational imprints of colossal collisions between supermassive black holes from the previous aeon. As our universe was born, the shockwaves from the death throes of its predecessor were stamped onto the fabric of the new one, leaving ghostly circles in the sky. If true, this would be a direct fingerprint of a universe that existed before our own, a pattern of inheritance written in the cosmic background radiation. It paints a picture of a cosmos without true beginning or end, a perpetual dance of creation and dissolution. The pattern here is not one of space but of time itself, an endless repeating loop. Our search for hidden order would then reveal the most profound pattern of all, that existence itself is cyclical, and every ending quietly contains the seed of the next beginning. But what could have planted those first gravitational seeds? The cosmic web gives us the large-scale structure, but the glittering nodes within it, the galaxies themselves, have a deeper mystery at their very hearts. Every large galaxy we observe, including our own Milky Way, hosts a supermassive black hole at its center. These are not the stellar mass black holes formed from collapsing stars. These are monsters weighing millions or even billions of times the mass of our Sun. Their existence presents a profound puzzle. According to standard models, they should have taken billions of years to grow, slowly feeding on gas and merging with other black holes. Yet, astronomers have found fully formed supermassive black holes shining as brilliant quasars in the incredibly young universe when it was less than 1 billion years old. There simply was not enough time for them to grow from stellar seeds. So where did they come from? One radical answer is that they were not born from stars at all. They are primordial. This theory suggests that in the first chaotic fraction of a second after the Big Bang, when the universe was a seething, dense soup, random quantum fluctuations in density could have been magnified by the universe's rapid expansion. In some of these ultra-dense regions, matter may have collapsed directly under its own gravity, bypassing the star formation stage entirely and birthing black holes of all sizes. Some of these could have been the supermassive ones we see today. They were not the products of the universe but its contemporaries born with it. If true, this changes the entire story of cosmic evolution. These primordial supermassive black holes would have been the universe's first permanent structures, forming before the first stars even flickered to life. Their immense gravity would have acted as cosmic anchors. As the universe expanded and cooled, vast clouds of hydrogen gas would have been irresistibly drawn toward these dark, heavy seeds. The black holes would have provided a central point for the gas to coalesce, spin, and eventually ignite into the first stars, creating the brilliant cores of the first galaxies. In this view, the black hole did not grow inside the galaxy. The galaxy grew around the black hole. This theory elegantly explains the pattern we see. The distribution of these primordial seeds, dictated by those initial random fluctuations, would have directly determined where galaxies would form and how massive they would become. The cosmic web's luminous nodes are not random. They are maps to where these ancient gravitational pits first opened in the fabric of spacetime. The supermassive black hole at the center of our Milky Way, then, is not a later addition. It may be the original architect, the silent, dark seed around which our entire spiral of stars slowly assembled over billions of years. Black holes may be the anchors of galaxies, but what anchors space and time themselves? For decades, we have imagined spacetime as a smooth, continuous stage upon which the cosmic drama plays out. But at the deepest quantum level, this stage may dissolve into something far stranger. A radical idea suggests that spacetime is not fundamental. Instead, it emerges like temperature emerges from the motion of countless molecules, from a hidden, underlying pattern of quantum connections. This is the theory that spacetime is built from quantum entanglement. Entanglement is one of the most baffling features of quantum mechanics. When two particles become entangled, they share a single quantum state. Measure one and you instantly know the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, as it seems to violate the cosmic speed limit set by light. But what if this spooky connection is not just a feature of particles, but the very glue that binds the universe together? This brings us to a profound conjecture with a deceptively simple name, ER equals EPR. It proposes a deep and unexpected link between two of Einstein's greatest ideas. ER stands for Einstein-Rosen bridges, better known as wormholes, theoretical tunnels through spacetime that could connect distant regions. EPR stands for Einstein-Podolsky-Rosen, the trio who first highlighted the paradox of quantum entanglement. The equation suggests these are not two different phenomena, but two sides of the same coin. A wormhole, a bridge in spacetime, might be the geometric manifestation of quantum entanglement. Think of it like this. Imagine two entangled particles as 2 points on a sheet of paper. In our normal view of spacetime, they are separate, connected only by that invisible, instantaneous link. But if you could fold the paper, you might see that the shortest path between them is not a straight line across the surface, but a tunnel through a higher dimension, a microscopic wormhole. Their entanglement is the quantum signature of that hidden bridge. This idea transforms our understanding of reality's fabric. If every quantum entanglement creates a tiny, Planck-scale wormhole, then the entire universe could be woven together by an unimaginably dense, dynamic network of these connections. The smooth, four-dimensional spacetime we experience would be a large-scale illusion, an average picture that emerges from this frenetic quantum web, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. In this view, when you entangle more and more particles, you are not just linking them, you are literally stitching new pieces of spacetime into existence. The very geometry of the cosmos, its capacity to have distance and separation, could be a direct result of the pattern of entanglement between all the quantum bits within it. Where entanglement is dense, spacetime is strongly connected, perhaps forming the matter we see. Where it is sparse or absent, you might get vast cosmic voids. This paints a stunning new picture of the cosmic web. Those great filaments connecting galaxies might not just be structures in space. They could be reflections of deep quantum entanglements on a cosmic scale, threads in the universe's fundamental circuitry. The hidden pattern we have been searching for, then, is not written in stars or forces, but in an invisible quantum lattice that literally knits reality together, one spooky connection at a time. Yet this quantum lattice stitching reality together presents an even more unsettling possibility. If consciousness itself can arise from complex patterns of information, as our brains suggest, then what is to stop the random fluctuations of the cosmos from spontaneously creating a mind? This is not science fiction, but a terrifying conclusion drawn from the cold equations of statistical mechanics. It is known as the Boltzmann brain paradox, named for the physicist Ludwig Boltzmann. The paradox begins with a simple, undeniable fact of our universe. Entropy, the measure of disorder, always increases. A cup shatters, ice melts, stars burn out, all moving from order to chaos. Yet, we find ourselves in a universe of breathtaking order, from structured galaxies to living beings. How can this be? The statistical answer is that while the overwhelming trend is toward disorder, random fluctuations can very rarely create pockets of order. Given enough time and an infinite or near-infinite universe, even the most improbable events become not just possible but inevitable. Now consider what is more probable. For the entire 13.8 billion-year history of our cosmos, with all its finely tuned constants and evolutionary chains, to fluctuate into existence from the chaos. Or for a single, self-aware brain, complete with false memories of a past that never happened, to spontaneously assemble from a random collision of particles. Statistically, the isolated brain is infinitely more likely. It is a simpler, smaller, more probable fluctuation than an entire ordered universe. The implications are existentially dizzying. If the math holds, then the number of Boltzmann brains floating in the void should vastly outnumber the brains that evolved in real, coherent universes like ours. Therefore, if you are a conscious observer, the odds are overwhelming that you are not a product of cosmic evolution, but a momentary accident, a brain that just popped into existence from the quantum foam, complete with the illusion of a body, a world, and a lifetime of memories. You are reading this script right now not because it is being spoken, but because a random fluctuation has generated the exact neural configuration of a person watching a video about cosmology. This thought experiment is not meant to be taken as a literal truth, but as a devastating critique. It highlights a profound flaw in some of our cosmological models, particularly those that posit an eternal or infinitely large universe. If such a universe exists, then the most common form of consciousness should be these disembodied, fleeting minds, not us. The fact that we observe a stable, ordered cosmos lasting billions of years is strong evidence against such eternal models. It suggests our universe had a definite beginning, a low-entropy starting point that makes our existence as evolved beings more probable than a phantom brain. The Boltzmann brain paradox forces us to stare into the abyss of randomness and ask the most fundamental question of all. Is our sense of a continuous, shared reality the ultimate truth, or merely the most convincing dream of a mind that has existed for less than a second, destined to dissolve back into the chaos from which it came? The Boltzmann brain forces us to question the very fabric of our reality, but another cosmic ghost has been haunting physicists for over a century. Its absence is a clue just as profound as any presence. This is the mystery of the magnetic monopole. Every magnet you have ever held, from a simple refrigerator magnet to the Earth itself, comes with an inseparable pair. A North Pole and a South Pole cut a bar magnet in half, and you do not get an isolated North and an isolated South. You get two smaller magnets, each with its own north and south. This duality seems as fundamental as nature gets, yet our deepest theories of the universe insist it should not be this way. When physicists developed grand unified theories, ambitious frameworks aiming to merge the electromagnetic, weak, and strong nuclear forces into a single, elegant description, their mathematics produced a startling prediction. These theories required the existence of particles that carry a single, isolated magnetic charge, a north pole without a south or a south without a north. A magnetic monopole, these would not be mere curiosities. They would be monstrously heavy, primordial relics, potentially as massive as a bacterium but concentrated into a single subatomic point, left over from the universe's first moments of unimaginable energy. Their existence would be a stunning confirmation of a profound symmetry in the laws of physics, revealing that electricity and magnetism are truly two sides of the same coin in a way our current, broken symmetry cannot show. So scientists began to look. They scoured ancient mica crystals for trails of damage, scanned the deep ocean floor, and built elaborate detectors, searching for the distinctive, powerful signature of a monopole passing through. The result, after decades, has been a resounding silence. Not a single confirmed magnetic monopole has ever been found. This glaring absence became a monumental crisis for the early grand unified theories. If the theories were correct, the hot, dense early universe should have produced these particles in staggering abundance. They should be as common as protons, and we should be swimming in them. Their complete invisibility meant something was terribly wrong with our story of the cosmos. The solution to this puzzle gave birth to one of the most important ideas in modern cosmology, cosmic inflation. To save the beautiful mathematics of grand unification, theorists proposed that the infant universe underwent a period of hyper-accelerated, exponential expansion, far faster than the speed of light. In a fraction of a second, a region smaller than a proton blew up to become larger than our entire observable universe. This inflationary spurt did not create more space for the monopoles. It stretched the existing space so dramatically that the primordial monopoles, which were formed in that initial chaos, were diluted to near nothingness. They were scattered so incredibly far apart that the chance of even one existing in our entire galactic neighborhood became vanishingly small. The universe, in a sense, hid the evidence. So the monopole's absence is not a failure. It is a powerful piece of indirect evidence for inflation itself, yet the dream of finding one has never died. Because if, against all odds, a magnetic monopole were ever detected, it would be a discovery of Nobel Prize-winning magnitude. It would be a direct messenger from the universe's first instance, a fossil from an era of perfect symmetry when all forces were one. It would prove that our deepest mathematical hunches about unity were correct, and it would forever change our understanding of the fundamental fabric of reality. We search for this ghost not because we expect to find it, but because its very possibility reveals a hidden pattern of perfection woven into the laws of nature, a pattern our universe has gone to extraordinary lengths to conceal. The universe seems to have played favorites from the very start. For every particle of matter that makes up our bodies, our planet, and every star, there should have been an equal and opposite particle of antimatter. Think of antimatter as matter's perfect yet deadly mirror image. It has the same mass but opposite electric charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy, leaving nothing behind. According to our best theories, the Big Bang should have created matter and antimatter in perfectly equal amounts. If that had happened, every particle would have found its antimatter twin, and the entire universe would have annihilated itself into a featureless sea of radiation in the first second. There would be no galaxies, no planets, and certainly no us, yet here we are. The fact that you exist to ponder this question is direct, living proof that something went wrong, or perhaps something went incredibly right. The scales were tipped. For every billion pairs of matter and antimatter particles that mutually destroyed each other in the early inferno, one single matter particle survived. That tiny 1 in a billion imbalance is all the matter in the cosmos today. Every atom you see is a relic of that ancient, unexplained surplus. This is the baryon asymmetry problem, and it is one of the greatest unsolved mysteries in physics. So what hidden rule broke the perfect symmetry? Physicists have identified 3 key conditions that had to be met for matter to win out, a checklist known as the Sakharov conditions. First, the laws of physics had to treat matter and antimatter slightly differently, a phenomenon called CP violation. It is a subtle preference in how certain particles decay. Second, the universe had to be out of thermal equilibrium, meaning it was not a perfectly smooth soup, but had changing temperatures and pressures that allowed the asymmetry to be locked in. And third, processes that change baryon number, which is essentially the tally of matter over antimatter, had to occur. We have observed CP violation in laboratory experiments, but it is far too weak to account for the vast amount of matter we see. So the hunt is on for the major event, the hidden process that did the heavy lifting. This search leads us into the realm of baryogenesis, the theory of how matter came to be. One leading idea is called leptogenesis. It suggests the asymmetry actually began not with the quarks that make up protons and neutrons, but with their lighter cousins, the leptons, like electrons and neutrinos. In the searing heat of the early universe, extremely heavy, hypothetical particles might have decayed, producing slightly more matter leptons than antimatter ones. Through a cascade of subtle interactions, that lepton imbalance could have then been transferred or reprocessed into the baryon asymmetry we live with today. It is a cosmic sleight of hand where the imbalance in one family of particles secretly funds the wealth of another. Another compelling theory is electroweak baryogenesis. It proposes that as the universe cooled and underwent a phase transition, similar to water freezing into ice, bubbles of the new, lower energy state of reality began to form and expand. The walls of these expanding bubbles could have created just the right out of equilibrium conditions, and through interactions with the Higgs field, the field that gives particles mass, they could have actively generated more matter than antimatter, filtering it into the universe like a cosmic sieve. The challenge is that our current measurements suggest this electroweak transition was not violent enough to do the job, unless there is new physics, hidden particles or forces we have not yet discovered. The quest to solve the baryon asymmetry is a search for the original crime scene. The moment the symmetry of creation was broken, it asks why the universe is made of something rather than nothing. Finding the answer would not just explain our existence, it would reveal a fundamental bias written into the laws of nature, a preference for stuff, for structure, for us. We are not here by accident, but because of a deep, hidden flaw in perfection, a crack in the mirror that allowed a material universe to step through. The universe's hidden bias toward matter gave us a world of stars and galaxies, but something even stranger is pulling on the largest structures we can see. Astronomers mapping the slow, drifting motions of entire clusters of galaxies have stumbled upon a cosmic current, a mysterious drift that defies all expectation. They call it the dark flow. Imagine dropping leaves onto a wide, calm river. Most will drift with the river's gentle flow, but if you see a group of leaves all moving steadily in the same unexpected direction, you would suspect a hidden current, a pull from somewhere downstream. The dark flow is that hidden current on a cosmic scale. By studying the cosmic microwave background, scientists can measure the subtle motion of galaxy clusters. The hot gas in these clusters leaves a faint imprint on the ancient light as it moves, a Doppler shift known as the kinetic Sunyaev-Zeldovich effect. When researchers analyzed data from thousands of clusters, they found something astonishing. The clusters were not just moving randomly from the expansion of the universe. A significant number of them showed a coherent bulk flow, all drifting in the same specific direction at incredible speeds, millions of miles per hour, toward a point in the sky between the constellations Centaurus and Vela. This motion persists out to billions of light years, far beyond the scale where the universe's matter should be evenly distributed and gravitational pulls should cancel out. Nothing within our observable universe is massive enough to create such a vast, coordinated pull. So what could be causing it? One breathtaking possibility is that the dark flow is the gravitational tug of something truly unimaginable, a colossal structure that lies beyond our cosmic horizon. Our observable universe is a bubble of space from which light has had time to reach us since the Big Bang. But the greater cosmos, if it is infinite or vastly larger, does not end at that horizon. The dark flow could be evidence that there is something out there, a supercluster of galaxies or a concentration of mass so enormous it makes our entire visible cosmos seem like a neighborhood, and its gravity is reaching across the void to pull on everything we can see. This idea shatters the assumption that our universe is isotropic and homogeneous on the largest scales. It suggests we are not the center of everything, but a small part of a much grander and possibly lopsided architecture. An even more radical interpretation ties the dark flow back to the very beginning. Perhaps it is not a pull from a structure in space, but a relic from a time before time. If our universe was born from a region of a larger, pre-existing reality that was not perfectly uniform, those primordial wrinkles, those initial gravitational tides, could have imprinted a preferred direction on the fabric of spacetime as it inflated. The dark flow would then be a fossil of that pre-Big Bang inhomogeneity, a cosmic memory of the larger multiverse from which our bubble emerged. This would be direct evidence that our universe is not all there is, but one bubble in a frothing sea of other universes, each with its own properties, and our local motion is a permanent scar from that violent birth. Skeptics, of course, offer more conservative explanations. They question the statistical significance of the findings or suggest unknown systematic errors in the complex data analysis. The evidence for the dark flow remains controversial, with some later studies failing to confirm it at the same strength, yet the mere possibility is transformative. If real, the dark flow points to a cosmos patterned on a scale we can scarcely comprehend. It hints that the grandest hidden pattern of all might be the shape of the multiverse itself, and we are just feeling the gentle tug of its distant shores. The dark flow hints at a universe tugged by unseen giants, but closer to home, a quieter mystery unfolded in the depths of our own solar system. For decades, scientists tracked the twin Pioneer 10 and Pioneer 11 spacecraft as they journeyed toward the stars. These robotic pioneers, having completed their missions to Jupiter and Saturn, were now coasting on inertia alone, their paths governed by the predictable clockwork of Newtonian gravity. Yet something was subtly wrong. As the probes sped beyond the orbit of Pluto, meticulous tracking revealed they were slowing down just a tiny bit more than they should have been. An incredibly faint sunward tug, an anomalous deceleration, was acting upon them. This was the Pioneer anomaly. It was a whisper of a discrepancy, equivalent to a force 10 billion times weaker than gravity on Earth's surface, but it was persistent and unexplained for years. The immediate suspicion was not new physics, but a mundane spacecraft effect, perhaps a tiny, uneven leak of heat or propellant providing a minuscule thrust. After a monumental effort to reconstruct every possible onboard system, the leading explanation settled on this thermal radiation, a gentle push from the spacecraft's own radioactive heat. The case seemed closed, a triumph of careful engineering over exotic theory. But the ghost of the anomaly lingered because it touched on a deeper, more profound question about gravity itself. Why does our understanding of this fundamental force seem to fray at the edges? The Pioneer anomaly was not alone. For some time, astronomers have debated other potential oddities in the outer solar system, slight mismatches in the orbits of distant trans-Neptunian objects that some argue hint at an unseen planet, a hypothetical Planet 9, or perhaps something else entirely. These puzzles have fueled a radical alternative to one of cosmology's biggest assumptions, dark matter. For decades, the dominant explanation for why galaxies rotate too fast and clusters hold together has been the existence of dark matter, an invisible form of matter that exerts gravity but does not interact with light. But what if we are wrong? What if there is no missing matter? What if instead our equations for gravity are incomplete? This is the premise of modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom in the 1980s, MND suggests that Newton's laws, and by extension Einstein's theory of general relativity, need a tweak at extremely low accelerations, like those experienced in the outer reaches of galaxies or by probes drifting in deep space. In MND framework, gravity does not fade with the square of the distance as neatly as we thought when its pull becomes incredibly weak. It transitions to a different, stronger regime. This single modification can astonishingly reproduce the observed rotation curves of spiral galaxies without invoking any dark matter at all. The pattern of stars whirling around a galactic center simply emerges from a revised law of gravity. The Pioneer anomaly, with its unexplained deceleration in the weak gravity of deep space, looked for a moment like a potential smoking gun for such a modification, a direct test in our own cosmic backyard. Proponents argued it was a sign that MND effects were real even within our solar system. The eventual thermal explanation was a setback but not a death knell for modified gravity theories. The debate is far from settled. Does the universe contain a hidden pattern of invisible matter, a cosmic scaffolding we cannot see? Or is the hidden pattern written into the law of gravity itself, a subtle code that only activates on the grandest, quietest scales? Each answer paints a drastically different picture of reality. One populates the cosmos with ghostly particles, the other rewrites the foundational script of physics. The true pattern may be waiting not in the distant flow of galaxies, but in the precise, silent drift of a human-made object into the eternal night. The pioneer's path was a whisper in the void, but the motion of entire galaxies is a deafening roar. Our Milky Way is not drifting in isolation. It is part of a vast cosmic river, and we are all being pulled toward a hidden destination. This is our local cosmic address, a supercluster of galaxies named Laniakea, a Hawaiian word meaning immense heaven. Laniakea is not a tightly bound cluster, but a sprawling web of galactic filaments, a gravitational watershed. Within it, 100,000 galaxies, including our own, are all flowing together in a grand, slow-motion current toward a single, mysterious point in space. That point is the Great Attractor. Imagine a colossal waterfall hidden behind an impenetrable curtain of mist. For us, that curtain is the Milky Way's own galactic plane, a thick band of stars, gas, and dust that shrouds nearly 20% of the sky from our view. This is the zone of avoidance, and directly behind it, in the constellation Norma, lies the gravitational heart of our local universe. The Great Attractor is not an object but a focal point, a center of gravity so potent it bends the paths of galaxies for hundreds of millions of light years. For decades, its true nature was a profound mystery, simply because we could not see through our own galaxy's dusty veil to observe what was there. What massive structure could wield such influence? With advanced X-ray and radio telescopes that can peer through the cosmic fog, astronomers have begun to lift the curtain. They found that the Great Attractor is not a single, unimaginably dense monster. It is a gravitational nexus, the core of the Laniakea supercluster itself. At its center lies the Norma cluster, a dense gathering of thousands of galaxies, and an even more massive cluster called Abell 3627. Combined, they form a gravitational anchor of staggering proportions, but the story does not end there. Our entire Laniakea supercluster, with the Great Attractor at its heart, is itself in motion. We are part of an even larger flow, pulled toward an even more massive structure hundreds of millions of light years away known as the Shapley Attractor, a concentration of mass considered the largest in our local universe. This reveals a hidden pattern of nested currents, a cosmic hierarchy of flows. Individual galaxies move within groups, groups flow into superclusters like Laniakea, and superclusters themselves drift toward the grandest gravitational basins in the cosmos. We are like leaves caught in a vast river system, moving with local eddies that are all part of a continental-scale watershed, drawn inevitably toward the sea. The Great Attractor is not an anomaly. It is a landmark in this hierarchy, a powerful reminder that the emptiness of space is an illusion. The cosmos is structured on every scale, from the quantum threads of entanglement to the continental drift of galaxy clusters, all woven into a single, dynamic, and flowing tapestry of gravity. That river of galaxies flows through a profound emptiness, but if you look up on a very dark, moonless night, you might see a faint, ethereal glow rising from the horizon after sunset or before dawn. It looks like a soft, triangular pillar of light, often mistaken for the first hint of sunrise. This is the zodiacal light, and it is not a trick of the atmosphere. It is sunlight scattering off countless trillions of dust particles that fill the inner solar system, tracing a path along the same flat plane in which all the planets orbit. This delicate glow is the fingerprint of our own cosmic neighborhood, a dusty disk we inhabit but seldom see. These are not just random specks of dirt. They are the fine powder of creation, the leftover debris from the formation of our solar system 4.6 billion years ago, and the ongoing crumbs from asteroid collisions and the tails of evaporating comets. This dust forms a complex dynamic system, a cosmic weather pattern within our own star's domain. Scientists study its distribution and composition like archaeologists sifting through ancient soil. The patterns in this dust tell stories. They reveal the gravitational pathways of planets, particularly Jupiter, whose massive pull can shepherd dust into specific resonant bands, creating concentrations and voids. They record the history of violent encounters in the asteroid belt, events that pulverized ancient rocks and sent their dust spiraling inward toward the sun. Most intriguingly, this dust is not sterile. Analyses of dust particles collected by high-altitude aircraft and space probes have found them to be rich in complex organic molecules, including amino acids, the very building blocks of proteins and life. This suggests that the zodiacal light we see is more than just a pretty glow. It is a continuous, gentle rain of potential. These dust particles, carrying probiotic chemistry, are constantly settling onto planets and moons. They may have seeded the early Earth with the raw ingredients for life, a process called panspermia on a local solar system scale. The cyclical patterns of this dust are also a clock. Major cometary disruptions or giant asteroid impacts can dump enormous amounts of new material into the interplanetary cloud, creating spikes in the dust density that might slowly fade over millennia. By modeling these cycles, we can look for echoes of past cataclysms in our system's history, events that may have triggered mass extinctions or, conversely, delivered new organic material to a waiting world. So the next time you are under a truly dark sky, look for that soft celestial triangle. You are not just seeing reflected sunlight. You are witnessing the faint, luminous trace of our solar system's ongoing construction site, a swirling reservoir of cosmic history and life's potential, painting a hidden pattern of dust and light across the vault of the night. The delicate glow of zodiacal dust tells a story of cosmic construction, but a new and dangerous pattern is now being etched around our planet, one of our own making. High above our heads, in the pristine realm of Earth orbit, a silent storm is brewing. It is not a storm of nature, but of human ingenuity and its unintended consequences. This is the growing cloud of orbital debris, a constellation of our own discarded technology. Every dead satellite, every spent rocket stage, every bolt and fleck of paint from a collision adds to this swirling shell of high-speed shrapnel. Currently, tens of thousands of trackable objects, and millions more too small to monitor, are whizzing around Earth at speeds exceeding 17,000 miles per hour. At those velocities, even a chip of paint can punch a crater in a spacecraft's window or disable a critical satellite. This debris field is not static. It is evolving into a pattern with a terrifying potential described by NASA scientist Donald Kessler in the 1970s. He envisioned a scenario now known as the Kessler syndrome. Imagine one major collision in a crowded orbital highway, like the one between an Iridium communications satellite and a defunct Russian Cosmos satellite in 2009. Such an event doesn't just create two pieces of debris, it creates thousands. Each new piece becomes a potential bullet, dramatically increasing the probability of further collisions. Those collisions would create even more fragments, triggering a cascading chain reaction. In a worst-case scenario, this runaway cascade could surround Earth with a dense, swirling belt of fragments so thick that it becomes virtually impossible to safely launch new spacecraft or operate satellites in certain orbits. The useful orbits for weather monitoring, global communications, GPS, and scientific observation could become impassable minefields for generations. This is not just science fiction. It is a clear and present danger, a ticking clock defined by the laws of orbital mechanics. The Kessler syndrome represents a profound shift in our cosmic perspective. For billions of years, the patterns around Earth were set by gravity and planetary formation. Now we have introduced a new, chaotic pattern, a human-made astronomical phenomenon with the power to trap us on our own planet. It is a hidden pattern with direct, tangible consequences for our technological civilization. The debris cloud follows its own orbital logic, concentrating in popular orbital lanes and forming rings and shells of risk that mission planners must now navigate. This has sparked a global effort in space sustainability, a race against our own litter. engineers are designing satellites to deorbit themselves at the end of their lives, burning up safely in the atmosphere. Concepts for active debris removal are being tested, from harpoons and nets to robotic arms and even lasers that could nudge fragments into decaying orbits. Treaties and guidelines are emerging to encourage responsible behavior in space. The pattern of orbital debris is a stark reminder that our influence now extends beyond the atmosphere. It shows that the hidden orders of the cosmos are not just things we discover, but things we can inadvertently create, and that the most urgent patterns we must understand and manage might be the ones we ourselves have set in motion. That human-made debris cloud is a pattern of our own ambition, but what if we are not the only ones imprinting order onto the cosmos? In the summer of 1972, a radio telescope at Ohio State University known as Big Ear was silently scanning the sky, listening to the static hiss of the universe. On August 15th, the telescope's recorder traced out a signal so powerful and so strange that when astronomer Jerry Amon reviewed the data printout days later, he circled the alphanumeric sequence and wrote a single, electrifying word in the margin. Wow, the WOW signal, as it is now known, was a 72-second burst of intense radio waves at a frequency of 1,420 MHz, a frequency that is naturally quiet because it is protected from interference, a band where cosmic hydrogen whispers. It came from the direction of the constellation Sagittarius, and it had the precise, narrow band signature that scientists had predicted for an artificial, extraterrestrial transmission. It was not like the broad, messy emission of a quasar or a pulsar. It was a clean, focused tone, a needle in the cosmic haystack, and then, as suddenly as it appeared, it vanished. Despite decades of follow-up observations, the signal was never heard again. The WOW signal remains the most compelling, unexplained candidate in the history of the search for extraterrestrial intelligence, or SETI. It is a ghost in the machine, a single, perfect data point that suggests a pattern of intelligence might be out there, broadcasting into the dark. The search continues, not for random noise, but for specific, mathematical patterns etched into the radio waves. Scientists listen for signals that defy natural explanation, like sequences of prime numbers. Why prime numbers? Because they are universal. The mathematical truth of a prime is the same on Earth, around a star in Andromeda, or in a galaxy a billion light-years away. A signal repeating the primes 2, 3, 5, 7, 11 would be a beacon of artificiality, a cosmic handshake saying, "We understand logic. We understand mathematics." We are here. Modern SETI projects use millions of home computers to sift through mountains of data, looking for these non-random patterns, these deliberate signatures in the chaos. They scan not just radio waves, but also for brief, powerful laser pulses, or even for the hypothetical megastructures of an advanced civilization, like Dyson spheres that might dim a star's light in regular, artificial ways. A confirmed detection would be more than just contact. It would revolutionize our understanding of intelligence as a cosmic pattern. It would tell us that the emergence of conscious technology building life is not a freak accident on one lonely planet, but a repeatable phenomenon, a natural phase in the evolution of a universe that tends toward complexity and awareness. It would mean the pattern of intelligence is woven into the fabric of reality itself, as fundamental in its own way as the spiral of a galaxy or the web of gravity. The silence so far is profound, but the search continues because finding that one patterned signal would answer the oldest human question of all, and in doing so, reveal the most meaningful hidden pattern of them all. We are listening for an echo of our own minds in the void. The profound silence that greets our radio telescopes is not just an absence of noise, it is a deafening question. With billions of potentially habitable planets in our galaxy alone, the cosmos should be buzzing with the signals of countless civilizations, yet we hear nothing. This glaring contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it is known as the Fermi paradox, named for physicist Enrico Fermi, who famously asked, "Where is everybody?" One chilling answer to this paradox suggests the universe contains a hidden and possibly deadly pattern of limitation. This is the theory of the Great Filter. The concept is simple, yet its implications are staggering. The journey from a lifeless planet to a spacefaring civilization that colonizes the galaxy is not a smooth path. It is a series of immense leaps or evolutionary steps. The Great Filter proposes that at least one of these steps is so incredibly improbable, so difficult to achieve, that it acts as a near insurmountable barrier. It is a cosmic bottleneck that prevents almost all life from progressing beyond a certain point, explaining the eerie silence. The terrifying part of this theory is the debate over where this filter is located in the timeline of development. Is it behind us or is it ahead of us? If the Great Filter is behind us, it means that the step we have already passed is the miraculous one. Perhaps the origin of life itself from non-living chemistry is astronomically rare. Or maybe the leap from simple prokaryotic cells to complex eukaryotic cells, which took over 1 billion years on Earth, is the universe's true bottleneck. In this scenario, the filter is a reason for celebration. It means we are extraordinarily special, a cosmic fluke that has already cleared the hardest hurdle. The galaxy might be littered with barren, lifeless worlds, and we are the lonely winners of the ultimate lottery, but the other possibility is far darker. What if the Great Filter lies in our future? This interpretation suggests that the step from an advanced technological civilization to a stable, interstellar species is the one that is almost impossible to achieve. The filter could be any number of existential catastrophes that inevitably befall intelligent life. It might be the invention of artificial intelligence that turns against its creators, or the unleashing of biotechnology that creates a planet-killing pathogen. It could be nuclear war, runaway climate change, or the unforeseen consequences of a physics experiment that unravels spacetime itself. In this view, every civilization reaches a technological adolescence, gains the power to destroy itself, and ultimately does. The silence of the cosmos is not a sign of our rarity, but a grim forecast. We look up at the quiet stars and see not an empty nursery, but a graveyard. This debate forces us to examine our own history for clues. On one hand, life appeared on Earth relatively quickly after the planet cooled, suggesting simple life might be common. On the other hand, we see no evidence of other civilizations or even their massive engineering projects anywhere we look. The pattern hidden within the Fermi paradox might be a universal law of fragility. It suggests that intelligence, when combined with technological power, contains the seeds of its own destruction, a self-limiting pattern written into the logic of evolution. Are we listening to a quiet universe because we are its first and only children, or are we hearing the permanent silence that follows a scream? The answer to that question will tell us whether the stars are our destiny or our epitaph. The profound silence of the cosmos might not be a sign of death, but of a deeper, more intimate connection. On our own planet, a radical idea emerged decades ago, proposed by chemist James Lovelock and biologist Lynn Margulies. They called it the Gaia hypothesis. It suggests Earth is not just a rock with life on it, but a single, self-regulating superorganism. The atmosphere, the oceans, the geology, and the biosphere all interact in a complex feedback loop to maintain conditions suitable for life. For example, when carbon dioxide levels rise and temperatures increase, plant life flourishes, pulling more carbon from the air and helping to cool the planet. It is a dance of balance where life itself actively shapes its own environment. Now, stretch that idea to the ultimate scale. Could the entire universe operate on a similar principle? This is the theory of a cosmic Gaia. It proposes that the universe might possess innate, self-regulating properties that favor the emergence and persistence of complexity and life. It is not about a conscious universe, but about a universe whose fundamental laws and constants create a stable platform, and where the emergence of life becomes a natural phase in its evolution, one that might even feed back to stabilize the whole system. Think of it as a grand cosmic version of a thermostat. The fine-tuning of the physical constants could be the initial perfect setting. The formation of stars that forge heavy elements, the supernova that scatter those elements to form planets, the gravitational sculpting of galactic habitable zones, all these processes could be seen as parts of a vast, unconscious machinery that consistently produces the ingredients for life. But the cosmic Gaia idea goes a step further. It asks if life, once it arises, might play an active role in this cosmic regulation on scales we cannot yet perceive. Could the collective consciousness or technological activity of civilizations somehow influence the universe's very structure or evolution over cosmological time? This sounds mystical, almost like a scientific pantheism. Yet, proponents argue it could be framed as a testable hypothesis about complex systems. We see self-organization and emergent behavior everywhere, from ant colonies to the global climate. The universe is the most complex system of all. Is it so unreasonable to think it might exhibit self-regulating behaviors we are only beginning to understand? The search for a cosmic biosphere, for patterns in the distribution of life-friendly planets, or even for correlations between the presence of observers and the stability of physical laws, could be ways to probe this idea. The cosmic Gaia theory blurs the line between environment and inhabitant. It suggests we are not just passengers in a dead universe. We might be participants in a living, breathing cosmos, part of a feedback loop billions of years in the making, where the universe grows life, and life, in ways we have yet to discover, helps to sustain the universe in return. This idea of a living, self-regulating cosmos suggests a universe in constant, dynamic motion. But what if that motion could become locked into a perfect, eternal rhythm? A ticking clock built not from gears, but from the very structure of matter itself. This is the startling reality of time crystals. To understand how bizarre this is, picture a normal crystal like a diamond. Its beauty comes from its spatial symmetry, a repeating pattern of atoms arranged in a perfect lattice that looks the same if you shift your perspective by a specific distance. A time crystal does something similar, but with time. It creates a structure that repeats not in space, but in time, oscillating between states in a regular, unending cycle, even in its ground state, its lowest possible energy configuration. This is a profound violation of an old assumption. In physics, if a system is in its ground state, it should be static, like a ball sitting at the bottom of a bowl. Nothing should happen without adding energy. A time crystal defies this. It is a ball that, even at the bottom of the bowl, somehow rocks back and forth forever, breaking what is called time translation symmetry. It is perpetual motion, not of a machine, but of matter's own quantum order. Scientists first created these exotic states in carefully controlled lab settings, using chains of ions or dense clouds of atoms manipulated with lasers. But the question immediately arose, could nature have forged its own time crystals in the extreme environments of the cosmos? The answer might be yes. One compelling candidate is the dense, ultra-cold heart of a neutron star. Here, matter is crushed into a bizarre quantum soup called nuclear pasta, where protons and neutrons are squeezed into shapes like spaghetti or lasagna sheets. Under such immense pressure and strange interactions, physicists speculate that these structures could spontaneously organize into a time crystalline phase, their components oscillating in a locked, rhythmic dance driven by the star's own ferocious magnetic fields or internal vibrations. Another potential cosmic cradle is the aftermath of the Big Bang itself. In the universe's first moments, as it cooled and underwent rapid phase transitions, fleeting regions of spacetime might have crystallized in time, creating ephemeral structures that pulsed with a primordial beat before dissolving into the expanding chaos. These cosmic time crystals would not be objects you could hold. They would be patterns of behavior, hidden rhythms etched into the fabric of reality under the most extreme conditions. Their existence would reveal entirely new phases of matter, ones where time itself becomes a structural component. This forces us to reconsider the nature of time. We think of it as a smooth, flowing river, but what if on a quantum level it has a granular, crystalline structure? Could the universe's most fundamental ticking be not the decay of particles or the expansion of space, but the silent, eternal oscillation of these hidden temporal lattices? Finding evidence of a natural time crystal would be like discovering a cosmic metronome that has been ticking since the dawn of creation, a hidden pattern written not in space but in the very heartbeat of time. Time crystals suggest a universe that can tick forever, but black holes present a paradox where time and information itself might vanish. This is the black hole information paradox, a conflict so deep it strikes at the heart of our understanding of reality. It pits two pillars of modern physics, Einstein's general relativity and quantum mechanics, against each other in a battle with no clear winner. According to general relativity, a black hole is defined by its event horizon, a point of no return. Anything that crosses this boundary, whether a star, a spaceship, or a book, is lost forever to the outside universe. The black hole remembers only three things: its mass, its electric charge, and its spin. All the intricate details of what fell in, the information that made a book and not a random collection of atoms, are seemingly erased, crushed into the singularity at the center. This presents no problem for classical physics, but quantum mechanics has a fundamental, unbreakable rule called unitarity. It states that information is never truly destroyed. It can be scrambled, transformed, or hidden, but it must in principle be recoverable. If you burn a book, the ashes and smoke seem like chaos, but a hypothetical superintelligence could, from all that scattered material, reconstruct the exact text on every page. The information is preserved, just in a vastly more complicated form. A black hole, according to relativity, does not just scramble information, it annihilates it. This creates the paradox: if quantum mechanics is correct, information cannot be lost. If general relativity is correct, information is irretrievably lost in a black hole. Both theories are spectacularly successful, yet they cannot both be right about this. The search for a solution has become a quest to find the hidden pattern that preserves cosmic information. Stephen Hawking himself ignited the modern form of this debate. He realized that black holes are not completely black. Due to quantum effects at the event horizon, they slowly emit a faint glow of particles, now called Hawking radiation. This radiation causes the black hole to lose mass and eventually evaporate completely over astronomical timescales. But here is the catch. Hawking initially argued that this radiation is purely thermal, like the heat from a stove. It is random noise carrying no information about what fell into the black hole. So when the black hole finally evaporates, all the information about everything it ever consumed is gone forever, violating quantum law. This was the paradox in its starkest form. Physicists have since proposed breathtaking solutions, each trying to preserve the hidden pattern of information. One leading idea suggests that Hawking radiation is not random after all. As particles are created at the event horizon, they might be subtly entangled with the interior of the black hole in an incredibly complex way. The information about the fallen book is not inside the black hole, but is imprinted pixel by pixel onto the escaping radiation. It is like burning a book, but having its entire text encoded into the specific flicker of the flames and the chemical signature of the smoke. To an outside observer, it looks like random heat, but the blueprint for reconstruction is there, woven into the quantum correlations. This process would preserve unitarity, but it requires a drastic rethinking of the event horizon. Another solution brings us back to the holographic principle. It suggests the information never actually falls into the three-dimensional black hole at all. Instead, it is encoded and stored on the two-dimensional surface of the event horizon, like data on a hard drive. The black hole's interior, including the terrifying singularity, might be a projection, an illusion created from that surface data. When Hawking radiation is emitted, it reads that data from the horizon, carrying the information away. In this view, the paradox dissolves because there is no mysterious interior where information gets destroyed. The three-dimensional drama of infalling matter is just a holographic movie played out on a two-dimensional screen. A more recent and radical idea is the firewall paradox. If information escapes via Hawking radiation, it forces a strange conclusion. The event horizon, which in Einstein's theory is a smooth, uneventful place you would cross without noticing, might actually be a wall of blazing high-energy particles, a firewall that would incinerate anything attempting to enter. This replaces one paradox with another, challenging the very principle of equivalence that is foundational to general relativity. Each proposed solution points toward a deeper, hidden pattern in quantum gravity, a set of rules that must govern the union of the very large and the very small. The information paradox is not just an academic puzzle, it is a clue. It tells us that our picture of spacetime is incomplete, that either our concept of a smooth, continuous universe breaks down, or our understanding of quantum information is missing a key piece. The fate of a single bit of information falling into a black hole may hold the secret to how the entire cosmos preserves its memory, maintaining the intricate pattern of cause and effect that makes reality coherent. While black holes threaten to erase information, another cosmic relic preserves a far older memory. A full second before the cosmic microwave background light was set free, the universe was a seething, opaque soup too dense for photons to travel. But another, far more elusive particle could already slip through the chaos. These are neutrinos. In that first second, a staggering flood of them decoupled from matter and streamed freely across the expanding cosmos. That ancient sea still surrounds us today. It is the cosmic neutrino background, a whisper of the universe when it was merely 1 second old, making it the oldest fossil in existence, even older than the famous cosmic microwave background. Picture this: every cubic centimeter of space around you, the room you are in, contains about 300 of these primordial neutrinos from the Big Bang itself. They are passing through your body, the Earth, everything at nearly the speed of light right now. They are the universe's silent, ghostly backdrop. Neutrinos are nature's ultimate ghosts. They have almost no mass, no electric charge, and they interact with ordinary matter so rarely that a neutrino could pass through a light year of solid lead without a bump. This makes detecting the cosmic neutrino background one of the most formidable challenges in all of science. We cannot simply point a telescope at it. Catching these ghosts requires monumental ingenuity. Imagine trying to hear a single, specific whisper in a stadium roaring with noise. Current experiments use ultra-pure, massive detectors, often buried deep underground to shield them from cosmic rays. They wait patiently for the 1 in a trillion chance that a relic neutrino from the Big Bang will strike an atomic nucleus with just the right energy to cause a tiny, measurable tremor. So far, we have not directly captured one, but why is this ghost hunt worth such immense effort? Because mapping the patterns in this neutrino sea would be like opening a time capsule from the universe's very first heartbeat. The cosmic microwave background shows us the universe at 380,000 years old, a toddler. The cosmic neutrino background would show us the universe as a 1 second old infant. Its subtle fluctuations, its slight variations in density and temperature, would reveal the gravitational landscape of the cosmos before anything else had formed. These patterns are a direct imprint of the primordial conditions, potentially allowing us to test theories of inflation with unprecedented precision and see if the seeds of the cosmic web were already woven into that neutrino fog. Furthermore, this background is not a static snapshot. It has been subtly sculpted by everything that happened afterward. As massive structures like galaxy clusters formed over billions of years, their immense gravity has gently warped and heated the passing sea of relic neutrinos, creating a faint imprint. By mapping these distortions, we could literally weigh the largest structures in the universe in a completely new way, offering an independent check on the amount of dark matter and dark energy. There is an even more tantalizing possibility. Some theories suggest dark matter particles, which also fill the cosmos, might occasionally interact with these relic neutrinos. If we could detect an unexpected pattern or a slight warming in the cosmic neutrino background, it might be the first indirect signature of dark matter revealing itself, not in a lab, but across the entire history of the cosmos. Detecting this background is listening for the echo of creation itself, a whisper so faint it has traveled for 13.8 billion years, carrying secrets of the first moment, the growth of everything, and the hidden hand that shapes it all. Far beyond the ghostly neutrino sea, in the frozen, silent outskirts of our own solar system, another hidden pattern is waiting to be solved. Astronomers studying the most distant objects in our cosmic neighborhood have found their orbits telling a strange and consistent story. These are the extreme trans-Neptunian objects, icy bodies that dwell in the dark realm far past Neptune, in a zone called the Kuiper Belt, but a handful of them have orbits that are not random. Their elongated paths are clustered together, their points of closest approach to the Sun aligned in a way that gravity from the known planets cannot easily explain. It is as if an unseen shepherd, a massive, distant world, is herding them into this peculiar orbital configuration. This is the heart of the Planet 9 hypothesis. The mathematical evidence suggests the gravitational pull of an undiscovered planet, perhaps 5 to 10 times the mass of Earth, orbiting the Sun at a distance 20 times farther than Neptune. Its year would be staggeringly long, between 10,000 and 20,000 Earth years. At such a distance, it would reflect virtually no sunlight, making it a true ghost world, a dark giant hiding in plain sight. The search for this phantom planet is a monumental game of celestial detective work. Astronomers are using some of the world's most powerful telescopes, like Subaru in Hawaii, to scan vast, dark patches of the sky where the predicted orbit might lie. They are looking for a single, faint point of light moving slowly against the backdrop of fixed stars. It is a needle in a haystack the size of the sky, and the haystack is almost completely black. But why does this matter for a theory about the universe's hidden patterns? If Planet 9 is real, its influence would reveal a profound architectural blueprint right here in our own solar system. Its immense gravity, acting over billions of years, would have sculpted the orbits of these distant objects into the clustered alignment we see today. This would mean our solar system's architecture is not fully known. We have a standard model of 8 planets formed from a smooth disk of gas and dust, but Planet 9 challenges that tidy story. Its extreme orbit suggests it could have been captured from another star system in the Sun's birth cluster, or perhaps flung outward by gravitational interactions with Jupiter or Saturn in the solar system's violent youth. Either way, its presence would be a fossil from that chaotic era, a permanent imprint of the dynamic processes that built our cosmic home. Finding it would do more than just add a new planet to our charts. It would confirm that gravitational patterns can hide major actors in the darkness, that even in a system we think we know intimately, a hidden architect can be at work, silently shaping the dance of smaller bodies across eons. The search for Planet 9 is a test of our ability to read the subtle signatures of gravity, to see the pattern in the chaos, and to discover that the final word on our own solar system's design has not yet been written. Our search for hidden architects has led us to the outer dark, but the most profound signatures of intelligence might not be planets at all. They could be stars that behave strangely, stars that have been enclosed. This is the concept of the Dyson sphere, a theoretical megastructure of staggering ambition. Imagine a civilization that has consumed all the energy its home planet can provide. To fuel its continued growth, it would need to capture the total energy output of its sun. Physicist Freeman Dyson proposed that such an advanced society might construct a vast swarm of orbiting collectors, satellites or habitats that completely surround their star, harvesting its light. This is not a solid shell, but a dense, coordinated cloud, a technological ecosystem operating at a stellar scale. The star would appear dimmed or even completely blocked in visible light, but the sphere itself, warmed by the starlight it captures, would radiate waste heat in the form of infrared radiation. To an outside observer, this would look like a star that is oddly dark, yet glowing with an unnatural, deep red warmth. This creates a searchable pattern. Astronomers are now scanning the sky for stars with exactly this bizarre signature, an immense infrared glow with little to no visible light. Several candidates have emerged, like the now famous star Tabby's star, which showed irregular, dramatic dips in brightness that some initially speculated could be caused by a partially built megastructure. While natural explanations like swarms of comets are more likely, the search itself reframes our hunt for cosmic patterns. We are no longer just looking for planets that might harbor life. We are looking for stars that have been engineered, for the industrial fingerprints of a civilization that has mastered its solar system. This ambition places such a civilization on a specific rung of a hypothetical ladder, the Kardashev scale. Proposed by astronomer Nikolai Kardashev, this scale categorizes civilizations by their energy consumption. A Type I civilization can harness all the energy available on its home planet. Humanity is not even there yet. We are currently a Type 0, still drawing energy from dead plants and fissile rocks. A Type Roman II civilization, the builders of a Dyson sphere, controls the entire energy output of its star. A Type Roman III civilization would command the energy of an entire galaxy. The scale is not just a measure of power, it is a potential hidden pattern of technological evolution, a roadmap that any advancing society might follow. If the laws of physics and the drive for growth are universal, then we might expect civilizations across the galaxy to eventually converge on similar solutions like capturing stellar energy. The silence of the cosmos could then be interpreted in a new light. Perhaps advanced civilizations are not broadcasting radio signals, they are quietly restructuring their stars, their infrared glow blending into the background heat of the universe. Our search for Dyson spheres is a search for this specific pattern of maturity, a look for neighbors who have grown up, settled in, and are now busy reshaping their corner of the galaxy into something profoundly, detectably artificial. That silent, ghostly neutrino sea is not the only thing permeating the void. In fact, true emptiness is a scientific impossibility. What we call empty space, the quantum vacuum, is not empty at all. It is a seething, bubbling ocean of unimaginable activity, the source of a power so vast it could rewrite the fate of the cosmos. This is the realm of zero-point energy. According to quantum mechanics, even at absolute zero, the coldest temperature possible where all classical motion stops, fields and particles still possess a residual, irreducible jitter. This is not energy from anything we can see or touch. It is a fundamental property of reality itself, a constant hum of virtual particles flickering in and out of existence, borrowing energy from the vacuum for fleeting moments before vanishing back into the quantum foam. This zero-point energy is not a small effect. Theoretical calculations suggest the energy density of this quantum vacuum should be astronomically, catastrophically large, enough to curve the entire universe into a microscopic knot in a fraction of a second. This presents one of the worst predictions in the history of physics, a staggering mismatch between theory and observation of over 120 orders of magnitude. Our universe is clearly not curled up, so where did all that vacuum energy go, or was our math profoundly wrong? This colossal gap is the cosmological constant problem, and its solution might hold the key to the universe's greatest secret. Some theorists propose that this seething quantum vacuum was the engine of cosmic inflation, that hyper-fast expansion in the universe's first instant. In this view, a specific kind of vacuum energy trapped in a field acted like a cosmic repellent, pushing space apart at an exponential rate until that energy decayed, transforming into the hot soup of particles of the Big Bang. The vacuum, therefore, would be the ultimate seed, the initial pattern from which all other patterns grew. An even more profound idea connects the quantum vacuum to the dominant force in the cosmos today, dark energy. Could the measured, gentle acceleration of the universe's expansion be driven by a tiny remnant of this vacuum energy, a faint echo of that inflationary push still lingering in the fabric of space? If so, then the quantum vacuum is not just a relic of the past, but the active sculptor of our future, slowly stretching the cosmic web into ever greater isolation. This leads to a breathtaking possibility. Is this quantum foam, this endless dance of creation and annihilation, the ultimate source of all structure? The random quantum fluctuations in this primordial energy could have been the very seeds that gravity later amplified into galaxies, stars, and planets. Every pattern we have explored, from the spiral of a galaxy to the branching of a tree, might trace its lineage back to these microscopic tremors in the vacuum. The universe, then, would be a magnificent interference pattern frozen into matter, born from the chaotic, creative churn of nothingness itself. We are not living in a universe of things, but in a universe of vibrations, a cosmic symphony played on the strings of empty space. That quantum symphony of empty space raises a profound question about the nature of reality itself. When a particle is not observed, quantum mechanics tells us it exists in a blur of all possible states at once, a superposition. But the moment we look, it snaps into one definite reality. What happens to all those other possibilities? The radical answer proposed by physicist Hugh Everett is that they do not vanish. They all become real. This is the many worlds interpretation. In this view, every quantum event with more than one possible outcome does not choose a single path. Instead, the entire universe splits or branches into multiple copies. In one branch, the particle is spin up. In another, newly created and equally real, it is spin down. This is not just for particles. Every flicker of quantum uncertainty, every choice made by a conscious observer, every random quantum fluctuation in a star becomes a fork in the road of reality, spawning new parallel universes. The result is not just many worlds, but an infinite, ever-branching fractal tree of all possible histories, a hidden multiverse of staggering complexity where every conceivable event plays out somewhere. The implications for cosmology are staggering. It suggests our observable universe, with its specific history and laws, is just one twig on an unimaginably vast tree. The wave function of the universe, a mathematical object describing its entire quantum state, does not collapse into one reality. It simply continues to evolve, and every term in its equation corresponds to a real, branching world. In this sense, the universal wave function is the ultimate pattern generator, weaving an infinite tapestry of realities from the threads of quantum possibility. This solves the measurement problem of quantum mechanics elegantly by removing the need for a special observer. There is no collapse, just perpetual branching. But it comes at a cost. It means that for every decision you agonized over, a version of you made the opposite choice and lives a different life. For every historical event that hung in the balance, there are universes where the other side won. This infinite replication can feel existentially dizzying, reducing our choices to mere branch points in a deterministic quantum equation. Yet it also offers a strange kind of cosmic optimism. No possibility is ever truly lost. Every dream, every avoided catastrophe, every road not taken is realized in some branch of the multiverse. The hidden pattern here is one of infinite potential, a cosmos so creative that it manifests every possible version of itself, ensuring that nothing, not even the most fleeting quantum whisper, is ever forgotten. The infinite branching of the many worlds suggests a cosmos built on pure possibility. But what if that possibility itself is shaped by a hidden, rigidly perfect geometry? The laws of physics we have discovered are not arbitrary. They are expressions of deep symmetries, mathematical patterns that remain unchanged even when we rotate a system or shift it in time. To unify these forces, physicists have journeyed into realms of mathematics so abstract and beautiful they seem like pure art, only to find they may be the blueprints of reality itself. At the heart of this quest are the exceptional Lie groups, particularly a structure known as E8. This is not a simple shape. It is a 248-dimensional mathematical object of stunning symmetry and complexity. Trying to visualize it is impossible for our three-dimensional minds, but we can understand its significance. In the mathematics of symmetry, E8 stands apart. It is one of a handful of exceptional structures that cannot be built from simpler pieces, a unique and fundamental pattern in the landscape of logic. For decades, theorists have been captivated by a tantalizing idea. What if the symmetry of E8, or structures like it, is the master symmetry from which all the forces of nature emerge? The dream of a theory of everything is to show that the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are not separate at all. They are different facets of a single, elegant symmetry that was manifest in the universe's first instant, then fractured as the cosmos cooled and expanded. E8 is so rich and complex that it contains within its geometry the potential to describe all known particles and forces in one sweeping framework. It is a mathematical cathedral where every particle, from the humble electron to the force-carrying gluon, could have its own designated seat, all related by the overarching symmetry of the whole. This is where the numbers themselves become strange. To build physics from such symmetries, you need the right number system. Our everyday algebra uses real numbers, and extending into complex numbers with the imaginary unit I was crucial for quantum mechanics. But to describe the intricate rotations and transformations in these high-dimensional symmetry groups, you need something even more exotic. Enter the octonions. If complex numbers are a two-dimensional plane, octonions are an eight-dimensional number system. They are the largest of the four normed division algebras, a rare and special family of number systems that includes the real numbers, complex numbers, and quaternions. Octonions are bizarre. They are not even associative, meaning that how you group numbers in an equation changes the answer. In most math, a times b, then times c, equals a times b times c. For octonions, that reliable rule breaks down. This makes them notoriously difficult to work with, but also uniquely powerful. Their strange, non-associative nature seems tailor-made to describe the peculiar behaviors of fundamental particles and the twisting geometry of spacetime at the quantum level. In some versions of string theory, the vibrations of strings that give rise to particles are naturally described using octonions. The theory suggests that the 10 or 11 dimensions it requires compactify or curl up in ways governed by these exceptional mathematical structures. The hidden pattern of the cosmos, then, might not be written in the language of forces or fields, but in the cold, perfect, and breathtakingly beautiful language of octonions and exceptional symmetries like E8. This is a universe where the logic of existence is not just mathematical, but a specific, rarefied form of mathematics that human minds happen to discover. It proposes that before there was matter, before there was energy, there was a sublime and abstract pattern waiting in the realm of pure reason, a pattern so compelling that to instantiate it was to create everything we know. That abstract mathematical perfection could have been the universe's first language, but life speaks a far more complex and messy dialect. If the fundamental laws are the same everywhere, could the same be true for life itself? This leads us to a theory that reframes our cosmic origins, the idea of panspermia. It suggests that life, or at least its essential ingredients, is not a rare miracle confined to Earth. Instead, it is a cosmic traveler, a hardy stowaway that can journey between worlds, seeding planets across the galaxy. The mechanism for this incredible voyage is written in the sky. Comets and asteroids, those ancient wanderers, are not just barren rocks and ice. They are cosmic couriers, rich with water and complex organic molecules like amino acids, the very letters in life's genetic alphabet. When these objects slam into a young, receptive planet, they do not just deliver water for oceans. They deliver a starter kit, the chemical precursors from which life could begin to assemble itself. We have seen the evidence: meteorites recovered on Earth, pieces of Mars, and samples from asteroids analyzed by spacecraft all contain these organic building blocks. The universe, it seems, is preloaded with the chemistry of life. The leap from these molecules to a living, reproducing cell is still immense, but panspermia proposes that this leap might only need to happen once in one lucky place. From there, the violent chaos of the early solar system could have blasted rocky debris carrying microbial life into space. Encased in protective layers of rock, these microscopic pioneers could lie dormant for millions of years, surviving the vacuum and radiation of space until their rocky vessel is captured by the gravity of another world. If that world has liquid water and a stable environment, the dormant spores could awaken and a new chapter of biology begins. This transforms the pattern of life in the cosmos. Instead of each planet struggling through the improbable steps of abiogenesis independently, life could spread like a cosmic infection, jumping from one habitable world to another via natural asteroid impacts. Our entire galaxy could be a single, interconnected biosphere, with a shared ancestry stretching back billions of years to a single genesis event somewhere in the Milky Way. But this theory has an even more provocative cousin, directed panspermia. What if the seeding was not an accident of celestial billiards but a deliberate act? This idea, championed by scientists like Francis Crick, suggests that an ancient advanced civilization, perhaps facing its own extinction, could have deliberately sent capsules containing microbial life to promising young planets. Using technology far beyond ours, they could have targeted star systems with Earth-like worlds, launching a biological legacy to ensure that their life, would continue elsewhere. In this scenario, we are not the random children of a chaotic universe. We might be the distant descendants of a purposeful act of cosmic gardening. Our DNA, the very code that defines all life on Earth, could contain a hidden signature, a maker's mark from that ancient civilization, waiting to be decoded in some universal pattern within our genetics. Whether natural or directed, panspermia paints a universe where life is not an isolated phenomenon, but a pattern of distribution. It suggests that the conditions for life, once met, can propagate across the vast interstellar distances, carried on the very comets and asteroids we once saw as harbingers of death. The hidden pattern here is one of biological continuity, a thread of life that may weave through the darkness, connecting worlds across space and time in a silent, living network. The idea that life might be a cosmic traveler is profound, but it rests on an even deeper assumption that consciousness is merely a latecomer, a happy accident arising from complex biology. But what if we have it backwards? What if consciousness is not the final product of the universe, but its very foundation? This is the most speculative and mind-bending frontier of all, the theory that reality itself is created or at least shaped by consciousness. We are not passive observers discovering an objective world. We are active participants in its very manifestation. This idea finds a strange foothold in the quantum realm. In the famous double-slit experiment, a particle like an electron behaves as a wave when not observed, creating an interference pattern of possibilities. But the moment a detector is placed to observe which slit it goes through, the wave-like behavior collapses. The electron acts like a single particle. The act of measurement, of observation, seems to force a definite reality from a cloud of potential. The Copenhagen interpretation, the standard view, treats this as a mathematical rule. But a more radical reading asks, what if the observer's consciousness is the key ingredient? What if the particle remains in a superposition until a conscious mind becomes aware of it? This interpretation suggests that at the most fundamental level, reality remains fluid and undefined until consciousness interacts with it, locking one possibility into place as the real world we experience. This quantum observer effect is just the tip of a vast philosophical iceberg known as idealism. For centuries, thinkers from the East and West have proposed that the material world is not primary. Instead, consciousness is the fundamental substance of existence. Matter, energy, space, and time are all phenomena within consciousness, not the other way around. In this view, the brain does not generate consciousness like a generator produces electricity. The brain is more like a receiver, a complex filter that tunes into and localizes a universal field of awareness. The patterns we have explored, the cosmic web, the fine-tuned constants, the mathematical symmetries, would not be external truths we discover. They would be the shared architecture of a cosmic dream, the consistent rules of a reality generated by a vast, perhaps infinite mind. This is not necessarily a religious concept of a single God, but could be a pantheistic or panpsychist view where consciousness is a fundamental property of the universe, like mass or charge, present in all things to varying degrees. The universe becomes a conscious entity experiencing itself through an infinite variety of forms, from atoms to galaxies to living beings. We are not separate from the cosmos. We are the cosmos becoming aware of its own intricate patterns. The implications are staggering. It would mean that the search for a hidden order is not a scientific quest alone, but a journey of self-discovery. The mathematical beauty we uncover, the eerie resonances between the brain and the cosmic web, the very fact that the universe is comprehensible to our minds could be seen as clues. They are hints that the observer and the observed are not separate. We are not looking at a painting from the outside. We are the brushstrokes, the canvas, and the painter all at once. This theory dissolves the hard line between subject and object. It suggests that the ultimate hidden pattern is the pattern of awareness itself, a luminous, self-reflecting tapestry where every star, every thought, and every law of physics is a facet of a single, conscious reality. It is the most intimate and the most vast of all possibilities, proposing that the universe's greatest secret is not out there in the distant void, but right here, in the very act of perception that makes the void seem distant at all. From the golden spiral in a sunflower to the cold equations of a simulated reality, we have journeyed across 30 breathtaking theories. We have seen a universe that might be a hologram, a computer program, or one bubble in an infinite multiverse. We have followed the ghostly pull of dark flow, questioned if we are Boltzmann brains, and wondered if consciousness itself is the foundation of everything. Each theory, from the elegant to the unsettling, represents a profound human impulse. We are not content with chaos. We are driven to find the order beneath the surface, the hidden signatures in the noise. This search is the very engine of science and the source of our deepest wonder. It is what turns the night sky from a scattering of lights into a map of mysteries waiting to be solved. So we turn the question to you. After this journey through the cosmos's secret blueprints, which one of these 30 theories reshaped your reality the most? Was it the idea that we live in a simulation or the haunting possibility of the Great Filter? Let us know in the comments below. If you are hungry for more journeys to the edge of understanding, make sure to subscribe. There are always more cosmic mysteries waiting just beyond the horizon. Until then, keep looking up, keep questioning, and never stop searching for the patterns hidden in the stars.